he is related to Sam in some way or another, at least mathematically. People can figure that out from the genealogical database. Anyway, it's a pleasure to introduce Dennis Sullivan from SUNY Stony Brook, who will talk about from topology to analysis.
Thank you. So, thanks for your invitation, Sam. Right. So, I kind of explained this. I borrowed Jesus Gonzalez's slide because it nicely summarizes a certain point of this stuff, and which I will get to at the end. So, okay, so this is probably for many of you a kind of favorite picture. You imagine you have a triangulation, and you can always form this dual object. And the secret of being a manifold, I've always felt, is the fact that this dual object is again a cell complex. And so somehow the secret is there, how to use it. And of course, this gives Poincaré's understanding of Poincaré duality. I think I call this the Poincaré dual cell operation, where this cell becomes this cell. Notice the boundary of this cell is these 2 points, and the dual of those two is the co-boundary of this cell. So that proves Poincaré duality. And staring at this, and notice there's a nice common subdivision, and people have been starting to write about this and call it the Kite Complex because the cells look like kites. So the idea in this talk is that this Kite complex, which is the intersection of any original cell complex, doesn't have to be a triangulation, and the dual cell complex, the minimal common subdivision, the Kite complex, has a certain combinatorial structure, which is the following. Let's think of the original, which actually kind of fits in spirit with the product cell complex functor in a way, combinatorial consideration. So let's think of one of the cells of the original decomposition, the red, and we label its vertices, its edges, and faces, and then we have the inclusions. So we have the partially ordered set, and the combinatorial structure I'm referring to is on this common subdivision. Related to this partially ordered set, and that's described here. So I took out just one piece and looked at the common subdivision on that piece, and let's see, I've left off one label. So all the cells of the common subdivision are just labeled by pairs of cells of the original. That's the combinatorial remark. So this vertex here, which is one I forgot to label, is labeled FF. So that's a pair of cells of the original. And these vertices are just vertex, 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 vertex. And then these vertices are edge, 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 edge. And this is face, face. So the vertices are filtered. And then these edges, this edge here is labeled E3F, which means corresponds to the inclusion of E3 into F. So you think of the inclusion as that arrow. And similarly, this edge is E1 contained in F. This edge is E2 contained in F. And this kite, which I didn't label either, is this is V3 contained in F. This would be V2 contained in F. This would be V1 contained in F. Right. So all the pieces are labeled by ordered pairs of cells of the original. Okay. When you do this to any triangulation, it turns out all the cells of this pair subdivision are cubes. What an interesting fact. It gives you a cubulation naturally attached to any triangulation. And then you can consider decomposition of manifolds into cubes, and then again you have the dual decomposition, but now the dual decomposition is again a cubulation. And the common subdivision is again a cubical subdivision. So we can quickly get into cubes by just applying this subdivision to any triangulation. And then as we further apply this subdivision, it's like these turtles all the way down, the cubes all the way down. You get cubes all the way down then as we further apply this pair subdivision. Okay, now what do we do with this combinatorial structure? So once you subdivide once, you have this extra combinatorial information. And the theme is going to be, we're going to consider subdividing, starting with one decomposition to cubes. And I'm thinking at the end, I'm going to talk about 3D fluid models. So I'm thinking of just a piece of 3 space. So I get really one cube, say with periodic boundary conditions. And then I'm just start subdividing it. And so at every stage, the subdivision is really the pair subdivision of the previous. And so I have the combinatorial structure available to me. So for example, if I'm at this level of subdivision defined by this size, there are 2 kinds of, because it is a subdivision of a previous coarser thing, there are actually 2 kinds of 2 cells. The 2 cell can either be on the face of a previous 2 cell or it can be slicing into a 3 cell. It turns out the combinatorics will distinguish between the way it works out between these 2 types of 2 cells. So that distinction is available to me. Okay, now, first thing you get from the combinatorics is that, well, these cells are like the morphisms of this category produced by the partially ordered set. So I can compose these morphisms. So there's a partial semigroup structure on the cells of the subdivision. There's a partial semigroup structure, just like the morphisms in a category have a partial semigroup structure, because you can compose 2 morphisms. So it's just, if you have a pair of cells, let me just say what this is. If you have a pair of cells, A contained in B, and B prime contained in C, this is equal to AC if and only if B equals B prime. Otherwise, it's not defined. So that's just composing the morphisms of the category. I can move from like this vertex into this edge, then from this edge into this face, and then from this face into this 3 cell. So I could compose like that. Okay, then given oh yeah, so I forgot to say, what is the goal? So I actually want maybe I'll comment about this picture. So the goal is to try to make some interesting part of analysis emerge from combinatorial topology or from topology. Some interesting part that hasn't been so infected before. Okay. That's the goal. So, okay. So I'm pretending I'm starting to proceed towards this goal. So we have this combinatorial structure. So then there's this partial semigroup structure. So then on the cells, then we can consider the linear span, the linear, the vector spaces generated by the cells. And I'm going to make a distinction. Sometimes I'll think of those linear combinations of cells as cochains. I'll call them cochains. And then I can apply the co-boundary operator. And sometimes I'll think of them as chains, and then I can apply the boundary operator. All right, so anyway, on the cochains, now I'll think of the linear combinations as cochains, then this semigroup structure immediately linearizes to an associative algebra structure. Namely, these are the generators, and you multiply them according to this rule. If B is not equal to B prime, the product is 0. So we get an algebra. So we define the semigroup, and now we define the algebra. So is that the definition clear? So I multiply the generators according to that rule. That's an associative algebra. And turns out the co-boundary, if you think of them as cochains, this is a, and notice the dimension of a cell with this labeling is the codimension. So a vertex, codimension is 0, FF is a vertex, EE is a vertex, the codimension is 0, so these are the vertices. In general, the codimension of the pair is the dimension of the cell. So this has codimension 2, a vertex in the face. EF, this has codimension 1, edge in the face, so it has dimension 1. So the dimension, and when you compose these pairs, the codimension adds. This codimension, if B equals C, plus this codimension is equal to this codimension. So it preserves the grading. Coboundary is a derivation, and this is a correct cup product functor from the point of view of topology. Okay, so once we subdivide, we have an associative cup product defined using the combinatorial structure that the being a subdivision entails. Okay. Now, the next thing is this star operation. So the theme here to try to get into analysis is to try to have a combinatorial replication for the ingredients of the tensor fields in differential geometry and geometric analysis. So I'm going to think of the Poincaré, Ailey Cartan, Hodge, Poincaré, Ailey Cartan, Hodge, Theorem, Hodge, stories. So we have differential forms, wedge product, exterior differential, and the Hodge star operator. So many interesting problems can be formulated in terms of those operations. So those are going to be the problems that will emerge, hopefully, from this combinatorial discussion having, or those can be addressed, so to speak. So, so let me say what the Hodge star, the analog of the star took some tinkering here, because I won't say, so here it is. Turns out in this discussion I'm going to be in dimension 3, and I only want the map that goes from 2 cochains to 1 cochains in dimension 3. So I'll just describe that one. The other ones have analogous descriptions. So there are 2 types of 2 cells. So the basis 2 cells in a subdivision, either the ones that penetrate like that or like that, tangent like that. And so the star operation is going to be, for type 2 guys, it's going to be this thing here. It's going to consist of there's an orientation issue, but it's going to consist of this edge plus this edge. That's going to be the star operation applied to that. So you can kind of think that this is telling you about this dual cell, and this would be the dual 1 cell to that dual 2 cell. Sort of the idea. And remember I said that the vertices are filtered by dimension. So I put this, in this 2 cell, I'm putting this, there's sort of 4 places I could have put this. I put it at the minimal point. Now for the ones of type 1, the filtration, these are the minimal, this is the minimal vertex here, and this is the maximal vertex. Here I put it at the maximal vertex. So this is the star operation, a picture. This has a slight difference from the usual story because this is an operator on the given cochain complex. The original star operation goes from the red to the green, so it goes from some place to someplace else. The usual way you write the star operator goes. So what I've done is made it act on the common subdivision by making this choice. Okay, I've been trying various choices, and this is one I like. Is that sort of clear? driving me nuts for years. This thing, star goes from something to something else, and in differential geometry, star goes from forms to forms. So this is how it's being addressed. This deviation in the analogy, direct analogy, is being addressed here. What? Cochain. Cochain. I'll call it a cochain. I want to call it a cochain. Yeah. So, okay. So the basis of the and I'm going to define it for two cochains going to one cochain. Okay. On the basis of two cochains, which is a basis element to be 1 on this 2 cell and 0 on all the others. So for that one, I want to get a 1 cochain. So it's going to be with an orientation. The direction should be either all this way or all this way. It's going to be 1 on this and 1 on this, but I got to choose the direction carefully, which I'm not specifying now. So that's it. But on this one, it's 1 on this and 1 on this coming out here. I used to take 1/4 of all 4 of them, but then the formulas got too complicated. Huh? From the picture. Look at the picture. I'm teasing him. He likes functorial things. See, the little nuance here is that I'm always using the fact that I'm not just only at one subdivision. I know it's obtained by one subdivision from a coordinate level. So I have that additional combinatorial structure. So I'm at this level, subdivision, but I can distinguish, there are 2 types of 2 cells. Actually, there are 3 types of 1 cells and 4 types of vertices, but there are only 2 types, and there's 1 type of 3 cell, just a 3 cell. But there are 2 types of 2 cells. So if they're tangent to a cursor 2 cell, that's type 1, and if they're penetrating the 3 cell, it's type 2. So that make a distinction. I mean, this is what you know, in Soren's talk yesterday, the axe, remember? All right. All right, so we have an algebra, we have the star operation. Okay. Now, in analysis, everything is about norms. Speed over the 3-dimensional volume, that's the energy, and then in the model for incompressible fluids, one can show the energy is non-increased. In fact, it's strictly decreased, except in special moments.
The norms here are going to be a little different. In fact,
anyway, the norms here are going to be a little different. In fact, they're going to be slightly stronger, and therein lies my hope. There's slightly stronger norms. They're going to be like the norm it's just going to be the L2 norm. I have a base vector space, so I just take all the generators to have norm 1, all the basic generators, and I just let them be orthonormal, and I take that norm. That's like an L2 norm. And in dimension 2, you have the L2 norm. You have the inner product given by the basis. That's the norm. And there's an analytical remark for those who appreciate it. These norms are stronger than the 3-dimensional L2 norm because if you imagine going to some, well, I won't say that yet. Let me go to the next. Let me discuss limits first. So, yeah, so there's a natural, we have all these subdivisions, so we have a natural, I guess I need some room, so I'll erase these pictures now. So we started at 6 after, how many minutes, 50? Okay, 6 after we started, or 7 after. So, to make the drawing faster, I'll just draw pretend I'm in dimension 2. So we have these subdivisions. We have these subdivisions. And of course, if you have a cochain here, you can get a cochain here by averaging. So the value here is the sum of the values here. That's the usual operation, right? And similarly, you can average this way. And now and the chain map goes this way. This guy breaks up into the sum of these 4 guys, and this guy breaks up into the sum of these 4 guys. Chain map goes that way. And then, let's just work about the cochain map. So we have just for fun, I'm going to call these expectations. In other words, you take these, you average these and put it there. That's like an expectation. It's an average. So composing these things all the way down, you have like many little pieces. You average them, and that's the value you put there. Expectation mapping. And then, so we have cochains here, and cochains here, and cochains here, and so we have the inverse limit. They now call this limit, but when I used to be in topology, this was called the inverse limit. You and I call it the inverse limit, right? Now they have the inverse limits and direct limits, and now they have limits and co-limits. I came back like Rip Van Winkle to topology, and what is this co-limit? What's the limit? You know, any category has a co-limit. Anyway, and even a homotopy co-limit. Anyway, this is just, I'll call it the inverse limit. And the inverse limit of all these cochains, I'll call that C. And then notice that the differential forms naturally live in here. If you have a 2 form, for example, you can integrate it over every little box, and the sum of the integrals is the integral here, so it's consistent with this map. So you get an element in the inverse limit for every differential form, and it commutes with D. That's Stokes' theorem, so everything is hunky-dory. And this has a D, and this has a D, so this fits in here, and this is an embedding, obviously. If you know all the integrals over all the little pieces, you know the form. And so, if you knew, for example, that there's a normalization which I have to. There's something about scaling. Things that are on scale. So these things have a natural area as you go down. You're going down exponentially fast, and a cochain is on scale if the value is some bound times the scale. Because when you integrate a bounded form, you're just going to get some bound times the area. It's not going to be any bigger, right? So the integrating differential forms fit inside the on-scale cochains. On scale. So the on-scale cochains and say bounded differential forms. There's a commutative diagram like that. One of the big problems in analysis is that the co-boundary of on-scale is not on scale anymore. D is an unbounded operator. So this is something like forms with distributional coefficients. Okay, so we have differential forms embedded in there, and then this remark about norms is that if you put the scale in to define the L2 norm, then the L2 norm on say 1 cochain, as you refine and fine, you're really going to have control over all of the values on every line, horizontal, vertical, so on. And see, knowing a function is in L2 on 3 space is weaker than knowing on every line in every direction it's in L2 restricted to the line. That's a different, stronger space. So the norms that are coming up here from topology are slightly stronger than the ones. If you just have a plasma of points in the manifold, you don't see this structure, and so you just go to the three-dimensional integral. Okay. And then there's some limit statements, which is, suppose, where are my notes? So somebody should have asked me a question that they haven't asked, an obvious question. But let me set you up to ask the question. So we have these, at each scale, we have cochains, and because starting from here on, this is the first one, I don't have it, starting from here on, this is the subdivision with that combinatorial structure, so I've defined algebra structures here, 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 and here. Yes? Sam. Are these maps of algebras? And the answer is no. They're not. They're not maps of algebras. That's why I call them expectations. You can have linear maps between algebras called expectation maps in the theory of C-star algebras and stuff. They're not maps of algebras. You have to do statistical analysis. The deviation, like the average of a variable, if you have two variables, A and B, and take their averages and then take their product and take the average, it's not the same thing. And the difference between is like the first cumulant or something, and there's some structure there called statistics, theory of statistics. Also, quantum field theory has this structure in it. Anyway, so that these maps are not maps of algebras, but there is a package of machinery you can stick on there called statistics. Okay. However, we'll try to get around that there are some limit theorems here, which is the statement, there are certain inequalities. See, if you were integrating a differential form over this edge, and you were integrating it also over this edge, if the differential form had some continuity to it, then say you go way out here, you're integrating this over some very tiny little edge, and then you move it over to, you compare these two little tiny edges, the two integrals. Well, there's some continuity in the differential form. This will only vary by how much you move, say, it's Lipschitz. And then this will be on the order of epsilon, if that's the size. This will be on the order of epsilon, but the difference will be on the order of epsilon squared, if it were a Lipschitz continuous form, right? So there's something called, you could talk about delta normal, where you apply that to a cochain, where you take its value on an edge and you move it normal. So an edge you can move 4 ways normally in 3 space, and then you can see how it changes. So there's some discrepancies there, and so it turns out that if you have delta n inequalities, I won't go into exactly what they are, but the inequality that you would get from any Holder continuous form would be adequate for this statement. Delta n inequalities imply that, see, I have these different products at level n and level n plus 1. I'll call this the product, A cup B, given by this structure here. Then you can take 2 compatible systems and form, so X and Y, and you can form X and Y, 2 compatible systems, and you can form, go to stage n of each one, and then form the n-fold product. And then you get a system of cochains. Now these won't be compatible because the maps are not compatible, right? However, you can still ask, is there a limit? If you have any system of cochains here, you can ask, is there a limit in here? Which means when you project the sequence down to any fixed level, it converges at that level. Okay? That's a slight generalization of what it means to be in the inverse limit. And then the theorem is this implies delta n inequalities on x and y implies the products delta n have a limit. And this is a variant of a theorem of Curvaire before 1960, and which I once read the comprendu note, and I can't find it now. And also Cheeger, after 1970, discovered a variant of this. So this is a variant of that. In fact, they put all the following statements together. First of all, the limit exists, and so you can now define x times y as the limit over n of xn and yn. Oh, this will be associative when defined. So if you have xn, x, y, and z all satisfying these inequalities, the limit's defined and it's associative at each level, so it'll be associative too. But the interesting thing is it's also graded commutative. Because you've added this coherence under translation. So going this way and this way can be compared. So you can get a commutativity. And it's consistent with wedge product. So if the x and y came from integrating forms that had enough continuity to give these inequalities, then this product would be the integral of the wedge product. Okay? So the forms can sort of be recognized in terms of continuity conditions on the cochain, and this product is consistent in the limit in that context with the wedge product. So the wedge product emerges from the combinatorics, but under the, I should have said this is a dense embedding because the forms map, every cochain can be realized by integrating some form. That's easy to show. So every cochain at every level. So it's dense in this topology. So you have this dense set and all these products that don't fit together, but under some hypothesis, the limit exists, but then it's nothing new, it's just the wedge product of differential forms. We have non-commutativity at the finite levels, but if we can make sense of the limit in this good case, then we get a commutative product, commutative associative product. And similarly, so this is like one limit theorem. There's a second limit theorem. Now you need more inequalities for this. You need normal and tangential inequalities. You need tangential inequalities. You can also, not only can you move a one simplex this way and see what's happening, you can also move a one simplex this way, tangentially. And you can ask that the values are coherent in some way. So tangential inequalities plus normal inequalities. As they say in French, the star operator plus exigeant. I mean, it requires more. Then the limit of the star n, so the star n was this thing, it's defined the same way at every level. At every subdivision, you define star, and I only define the one for 2 to 1. Limit of star n exists and is consistent with the Hodge star. Hodge star. Oh, well, star and forms. Okay, so these are two kind of elementary theorems, although the proofs are a little complicated combinatorially, but they're sort of straight. You just brutally compute, and then I think there's a computation with 16 terms, and you have to kind of pair them off, and then use deep properties of the geometric series, you know, and then you can prove that. That's about. It's like a, you know, easy theorem. But Okay, so that much emerges. Okay. So that's sort of the setup. I imagine cubulation of a manifold, and then I start subdividing it. And for those who've had a little experience in some of this geometry and analysis of social subdivision, there's the notion of the barycentric subdivision is a bad subdivision because it's not combinatorially finite locally and not geometrically finite. You get long, skinny things. But these subdivisions are beautiful. As you go down, the combinatoric stays locally finite, and the geometry stays locally finite. So that's another reason to recommend them. And so you can, talk about limits without extraneous difficulties getting in the way. Let's see. So we have this manifold. We have this combinatorial picture, and then under appropriate circumstances, we have limits, and it fits with differential forms. So we've gotten differential forms emerging. Now, so let's go to the second part, 3D fluid models. So I've been sort of fascinated with this. My history was I was working in topology till sort of, and in the beginning of the 90s, I found out about this amazing fact that the equations that they write fluid mechanics down, the model, the continuum model for fluid motion doesn't have a complete mathematical theory. Namely, there's this, you can start with smooth data, and they don't know whether in 1 second it just might, you're standing at a point, you have a smooth vector field, you let the fluid equations go, and you're standing here. Maybe before 1 second elapsed, the solution that was here blows up. That's possible. That's a famous question. And I was astonished by this because engineers use this, and I don't want to talk about this too long now. But anyway, it's still an open problem. Then even more, so that's like, that's the pure side. There's the PDE, continuum model of fluid motion, and the pure theory of it is basically missing in dimension 3. In dimension 2, the theory is actually the pure theory about existence and uniqueness is perfectly well developed, and in fact it's equivalent to a PDE that we studied in dynamics, which is called the Beltrami equation. It's equivalent. It's not the same. There's a metaphor that takes you from the data here to the data here, and the proof here to the proof here. And it's exactly the same analytic considerations are true, and the same theorem arrives in both places. Anyway, so I thought, gee, I know that, and I know all about dynamics. Let's see, what's the problem here? I wasn't going to try to solve it. What's the difficulty? Anyway, you find out the difficulty is in these norms. And you can find that out in about 6 months. And you can see why they didn't solve it. And so, and scouting around a little bit, one person in France told me that, well, this equation is sort of derived from more fundamental particle equations, Boltzmann equations, and only under assumptions that certain statistical things happen, which are not proven. And then you can derive these equations. So it's like but thermodynamics works, so it's everyone believes this derivation, and they seem to be good models and they're used. But this person in France, Claude Bardot, said that no progress will be made in this continuum model unless you make progress in the underlying equations that are used to derive the model, Boltzmann equations. So I'm waiting around for them to make progress for the last 20 years. They haven't made any. And so it occurred to me, well, this is well, okay, then another point was that I forgot to say in dimension 2, the theory is fine, but the applications are not fine. It turns out the thing is so sensitive that the moduli of continuity on the data gets quickly deteriorates. And So the computational methods quickly deteriorate. So in fact, they don't have good ways of computing in dimension 2, even though the theory. So this side, even in dimension 2, is open to negotiation. It's gotten better because of the power of computing, and in fact, they're interesting results, but they actually are even contradicting the theory somehow in some cases when you drop the friction. So anyway, even in dimension 2, that side's okay, but that side's not okay. And then in dimension 3, both sides are open. So, and another person I interviewed about this, Galavati, he's a physicist, so he said, this thing I was just saying, he wants to make an algorithm so if you're standing at some point and you have your vector field around you and you let the Navier-Stokes equation go for 1 second, you want to compute the vector at this point, 1 second later. That's all. Make an algorithm to do that. Give your vector field, make an algorithm to compute 1 second later. So being able to do that solves both sides, because not only then can you show the solution exists and is unique, but you actually have a way of computing it. So he's actually very ambitious, trying to do both sides. So I thought, well, what if this thing doesn't converge, does blow up mathematically? It's a very good model for fluids. They use it all the time. And if you look at fluids, like fountains and flows and creeks and stuff, you see patterns. When you wash the dishes, you see patterns, you know. And these are observations at a finite scale. So it occurred to me, if the wonderful thing were true and there was a solution to both things at once, and there were these algorithms, what are they? What are these algorithms? So, and then it occurred to me, you don't really have to do the pure side, because fluids are out there. They know what to do. You would just like to have algorithms that compute what the fluids are doing, so you can use it to predict weather and stuff like that. So that's there. I mean, you may not be proving anything about this math problem, but you may produce algorithms that can be useful. So I started saying, well, let's just make algorithms. Well, how do you make algorithms? Well, you obviously have to chop the space up into finitely many pieces, and you know. You have to put finite things in the computer. So then you get thrown right back into combinatorial topology or something like it. Now the applied mathematicians know these pictures obviously, but they don't know about the mathematical structure of cup product and star operator, or they know star operator. And they know wedge product. They don't know cup product. They don't know Steenrod's work. I mean, so I thought, well, I know something they don't know, so maybe it can be used. So Steenrod's work is embodied here because this cochain multiplication is defined over the integers, and it's not commutative. Definitely not commutative. Right? So let's just don't worry about it. Just don't worry about this. Just try to make some algorithms. Okay, well, the fluid is described by, the continuous fluid is described by a velocity field, and in the presence of a Riemannian metric, that's the same thing as a one form. So we can take that one form and integrate it over every edge at every level of decomposition. So we can convert the continuous data into our world. So just forming the cochain at every level. Okay, then now we want to go to each level. So on a computer, you can only go so deep, and then you have to stop. You can only go, and then, in fact, I've been talking to Jim Glim at Stony Brook, and they sort of go as far as they can, and then they have one subdivision, and then they compare things They go almost to the limit of their things, and they have one more subdivision. They compare algorithms at the two subdivisions. So the algorithm is just going to be, I'm just going to go to any level, take a cochain, think of it as having come from a velocity field, being finite averages. This idea of taking averages goes back to Reynolds, and then the applied mathematicians make algorithms out of these averages too. There's a little discussion about that, which I don't have time to give. But it involves defining a multiplication because it's a nonlinear problem, but their multiplication is always non-associative, as far as I know. So that's one difference, and then so this multiplication I'm going to use as associative. Now, there's a little bit of physics to derive the continuum equation. I'll just indicate, and all the difficulty and intricacy of fluid motion arises from the nonlinear term. And so you have some equation that says the time evolution is basically the sum of two terms. This is, I'm doing three-dimensional Navier-Stokes equation, incompressible. So there's a nonlinear term and a linear term. This is a helping term. It's helping you, this linear term. There's a coefficient of friction here, so the friction's helping you. This is related to the friction. And then this nonlinear term is built out of two parts. One is kind of an actuarial consideration, and one is Newton's laws. Newton's law says particle fluid's moving along, has a velocity, a direction, and its acceleration is produced by the force on the particle, the change. So that's there. So you have like in a test body or a test neighborhood, you have a lot of particles moving in and moving out of the neighborhood. And if you had any quantity attached to the particle, like its temperature or something like that, there would be a change in the temperature you would observe here just because some cold particles might move in and some hotter ones might move out. So there's the temperature and then the temperature might actually be changing on the body according to some internal thing that's happening. But any quantity, there's an actuarial issue about the quantity, the intensive quantity, because different kinds of particles are moving in and moving out. And that's subject to the velocity. Okay, the velocity field will move things in here and move some out here. And I'm in the incompressible case, so everything is going to be volume preserving. So the amount of stuff that moves in equals the amount of stuff that moves out. That's why I'm observing. But hotter particles may have replaced colder particles. So the temperature would change just because the population changed. Like a neighborhood gets richer. A poor neighborhood gets taken over by richer people. Okay, poor people move out and the rich people move in. Now, we're going to apply this consideration to the momentum, which has three components. And it's proportional to the velocity because the velocity, it's volume preserving, so that the mass doesn't change. So the momentum and the velocity are proportional. So I'll say momentum, I'm really thinking velocity. So the x component of the momentum, the y component, and the z component are like the three temperatures I was just talking about. Each one is affected by what moves in and what moves out. Some people wealthy in x momentum may move in, some poor in x momentum may move out, and then the x momentum increases because of that. So there's a term you put for that consideration. And that term, when you write it out, so let me write down, this is, I'm going to call it dx dt. So x is going to be the one cochain or the one form corresponding to the velocity. So there's going to be, so momentum and velocity are the same, so the velocity, so to speak, is acting on itself. The three components of velocity are the momentum. The velocity is acting on itself. And this term is this neat little term 5 years from 92 or 3 to late 90s, I used to write this down every morning at breakfast. See if I can remember what it is now. So that's the, see that's, it's the velocity is acting on itself. It's a quadratic term. Velocity is acting on itself. Now, this term is not necessarily volume preserving, and you want to keep this volume preserving condition. So you look at the one forms, it'll have a Hodge decomposition into the volume preserving part and the gradient part. So what you do is you subtract off the gradient component, which is called dP. dP is called the pressure function. But anyway, it's just the gradient component of this. You subtract that off. And this pressure is like when, if more guys are moving in this way and fewer are coming out that way, there's some pressure on the guy standing here to move that way. The crowd's coming in this way, it's open this way, so there's pressure. So the volume preserving, so the Newton's law is coming from this term here. And then it turns out the friction, if you make an isotropic linear response assumption, is just some constant times the Laplacian of x. And this is a positive constant. Friction is a negative. So negative. Yeah. And you could also think of, okay, so that's the Navier-Stokes equation. So we'll make the same analysis to get our approximate one. We'll see what comes in, what goes out. We have the Hodge decomposition. In fact, D and del are adjoint operators for our Hodge decomposition because the transpose of del is D and so on, right? Oh, I was, geez.
We want to wrap things up.
I'm 2 minutes over. Okay, so take one more minute. Okay, that took too long on that. So I'm going to just write at level n. So the nth level Navier-Stokes equation is just going to be dx dt. And this will be acting in a finite dimensional vector space of cochains. It's an ordinary ODE. So it's going to be the star at level n. And then I'm just going to write x. I use the product at level n. And I use the co-boundary. And then you project in the Hodge decomposition onto the co-exact part. That's what this term is, just the projection. And then let's let nu be 1. And then minus the, so the volume preserving condition becomes boundary x is 0. Then we write the Laplacian. The Laplacian is boundary delta plus delta boundary. This term is 0 because Laplacian x is 0. And then it's just minus co-boundary of x delta. Okay, so this is the Navier-Stokes equation at level n, and so the proposal is that you would kind of derive this as a metaphor from continuum 1, and then the idea is you can directly go to applications and start computing and see if it fits with observations or not. Thank you.
We have time for a quick question.
For the ordinary differential equation, this
The continuum equation?
Yeah, at level n, solutions exist for all time for this equation.
Yeah, so you're asking, does this equation have solutions for all time? Well,
It's a complete flow.
so I don't know. I don't know. In fact, I mean, in further notes, which I'm not going to use, is there's a nice computation that the energy is preserved in the continuum case, and it uses all the properties that we have, uses the associative law and everything else, and then at one crucial point it uses the commutative law for wedge. And so when I compute that same computation, I get this extra term with an x times x. And currently I'm in the midst of a battle with that term. And the idea would, of course, be to try to make this exist for all time, at least for some subset where you have certain properties that would be the goal. But
Okay. Okay. One question.
but give him the thing so I can't hear. Yeah.
Can you discretize your discussion on flows along a one-dimensional graph?
What do you say?
Graph, right?
I don't know. I haven't thought about it, but I'm a little worried because incompressibility in dimension 1 kills the problem a little bit, I think. Then you have to have particle splitting. But I'm really tuned into it being a manifold, so haven't thought about it. But it's a nice question.
Okay, I think we'll stop here. Thank the speaker again.
I don't like
And there is no break. We continue with the next speaker.
stops the thing too soon.